And for this chapter, I just want to, emphasize or what we're assuming here is that individuals and these consumers are rational. You might think, oh, who's actually rational? What that means is, so if we talk about two goods, an apple and a banana, we can rank them. All of us kind of have our own preferences. And we can say either an apple is better than a banana is better than an apple, or they're the same. They're just as good as one another. You like them equally. So we say people are rational when their choices are pretty consistent. Like if, say, they're the same price, even though typically not, but say they're the same price. A person who likes apples more will typically buy more apples than bananas. And as long as they're kind of consistent with that, they're not changing their preferences, every day, we say they're rational. And that makes it easy to work with. Now, some of these notes we're going to skip through, and they're kind of math wordy, so you don't have to go through them or know anything. Yeah, to be honest, we don't even need to go through them. They're talking kind of about how we set up this next part mathematically. Again, I'm not going to ask you these things. But what I want to go over, and talk about first, is, remember, in consumer theory, which is what we're talking about starting in chapter 2, consumer theory is looking at individuals. And we know that individuals want to maximize their utility. So in this chapter, we're actually going to put utility into a functional form to study. So this is going to give a value to our bundles that we're looking at. So we're getting kind of like a number for utility here. So if we have 5 apples and 2 bananas, how happy does that make us? That's what we're trying to think about. And you're probably like, oh God, I don't think like that. And nobody does, actually. Nobody thinks about like these numbers, and that's okay. What we're doing is we can look at people's individual behavior, maybe how they shop, and we can form a utility function from that. Like maybe, you go to ShopRite and you put in your phone number for like discounts. Yeah, we can use that data possibly to form these functions. And so we're going to have a level of utility basically for every bundle. I'm just going to show you in general. These utility functions are going to have different shapes or different forms, but I'm going to talk about one, and let's talk about this. This is going to be what we call an indifference curve. So I'm just going to call this IC1. Difference curve. I am not spelling well today. So this IC indifference curve. This is showing all bundles, so bundles of X1 and X2 that yield a certain level of utility. So this indifference curve I just drew, maybe that's associated with the utility of 100. I'm just making this up on the fly. But that means every point on this curve gives the consumer exactly 100 units of utility. So they're giving them equal satisfaction or happiness. And we say then the consumer is kind of indifferent between them. Since they're giving them the same happiness, you can choose this point or this point or this point, and you don't really like one more than the other because of this utility. So these indifference curves and utility functions, they're going to be in different forms. So this is one example, and we'll talk about what that looks like coming up, or what that means when it's like this. But I'm going to talk about another one because it might be good to see one with numbers. Okay. So let's give an example. Maybe we have u of x1 comma u of x2 equals x1 plus x2. So this is a relatively simple function, but it's their utility function, x1 plus x2. And maybe we want a certain level of utility equal to 12. Now what I want you to do is I'm going to ask you a question and go in your chat and maybe write down some answers. There's going to be a couple of different answers, but don't send anything in. What I'm asking is, we have our utility, x1 plus x2 equal to 12. Think of different bundles of x1 and x2 that will yield 12 units of utility. Think about that. Don't send it in just yet. But amounts of x1 and x2 that give us 12 here. There's definitely more than one answer, so you can, write down a few if you'd like. If you think about them, give you a few more minutes or a few more seconds. All right, if you have something, send it in. No? Okay, yeah, there we go. So I have a few 12 and 0, and what that means, so x1 would be 12, say, and x2 is 0. You add them together and you get 12. 1 and 11, 2 and 10, and Catherine, 6 and 6, 5 and 7, 4 and 8. All of these are correct. So what this does is we can create this indifference curve, and it's made up of all of these different points that we just said. This is like 12 and 0, and 0 and 12 here, 6 and 6 in the middle. All of these points that we said are on this indifference curve. So I'll call this IC1, indifference curve 1, and that is where utility is equal to 12. All of these points. And again, because each point here gives us 12 units of utility, we say we're indifferent between them. We like them just as much as each other. So like we like 6 and 6 and 12 and 0 the same amount. Okay, we're happy with those numbers, those combinations. Now I want you to think about, let's say we want to draw an indifference curve for where the utility is 16. How do you think that's going to look like compared to this? How would we draw it? Or would it be maybe higher or lower than the first one, the purple one? Would it have a different slope maybe? Since then the chat said increase. Anybody else? Another increase. Yeah, that is correct. This would be something, it's not very great, So this pink would be like IC2, where the utility is 16. It will be higher. The slope should actually be the same. I'll make a note there since it doesn't look like it. We'll talk about slope as we, in a minute. So this indifference curve, because it yields more utility, it's on a higher level. So like say we had the 6 and 6 point here, like we had before. But now we go up to the next indifference curve. Well, that means even if we have the same amount of x1, we have a greater amount of x2, maybe 10. And that actually works out. So it's 10 plus 6 is 16. Because this point here was 6 and 6, now we have 6 and 10, having more of this one good is going to make us happier. So we're jumping to a higher indifference curve and we're getting more utility. So every point here gives us 16 units of utility, whereas down here it's only 12. As we go higher, we get more and more utility. So we can get, any number up there. Anything lower though, we would get less. Like the U is 6. So something lower will have less utility, make us less happy. And I want to note that, we definitely don't think of utility in values. Like I said, we can estimate it based on behavior, but the number really doesn't mean anything. So like I say, these two goods give us 12 units of utility. That doesn't mean anything in the real world. It's just a level of happiness that we can compare to other bundles. Whereas like up here, these bundles give us 16. It's not that this is so much better than the first one, but it is better. It's not, we don't know how much better. It's just, makes them happier. So these numbers are kind of just placeholders for these values that we really can't estimate because nobody thinks in numbers of utility. Well, for the most part, nobody does. But we know what makes us happy and what we want to buy. Okay. So I want to emphasize that every bundle on an indifference curve yields the same amount of utility. Kind of like a definition too. So not like with the indifference curve, all yield the same level of utility every point, and we're indifferent to them. If anybody needs more time on this, let me know, or else I'm going to make a new slide. Next thing I want to talk about is slopes of these indifference curves. Slope really. Now, what we call the slope is known as the marginal rate of substitution. Or the MRS. So if I say MRS, I'm talking about a slope here. But it has a meaning. This meaning, or this slope, shows the amount of X2 a consumer is willing to give up for one more X1. We all have different numbers here. We all have probably different preferences. But it's like we're looking at if we want to buy another unit of this X1. Maybe X1 is coffee and X2 is energy drinks because we're all tired in the morning. And we're buying so many a week, this slope is going to say, well, what if we want to buy one more coffee? How much energy drinks are we going to give up? It might be 1 and 1. It might be more though, or less. So we might have a different number. Again, it's different for all these consumers that we're looking at. We're kind of looking at like either aggregate, kind of an average, or maybe just one individual too. So we don't have to think about different people. Now the MRS has an equation like everything else. Marginal in economics always means derivative. So what we're finding, or what the equation is it's the marginal utility with respect to x1 over the marginal utility with respect to x2. And we just expanded it, made it more complicated because we didn't really define these before. But we're talking about derivatives, and what this looks like on top, this is the derivative of the utility function with respect to x1 over the derivative of the utility function with respect to x2. So we have two partial derivatives here. And as I'm going to show you as we go forward, when we have different utility functions, different types, there's going to be different ways to solve this. And sometimes there's like a trick you can use, which makes things easier. So we're going to kind of look at this now. So let's say we use this example, the utility is equal to x1 plus x2. And I want you to find the MRS. Do this in steps. So I'm going to look at the top. du dx1. We're taking the partial derivative with respect to x1. You can tell me what that is here. Chat is fine too, if you know it.
1.
Yeah, then good. So just 1. And it's just 1 because when we do the partial derivatives, remember x2 here is a constant. And since there's not an x1 with it, like multiplied, that just goes to 0. So we're looking at the derivative of just x1. And we always just take that constant term, so just 1 in this case. Then we do the partial derivative with respect to x2. And what number is that? What amount is that?
1.
Devin, I think you said 1. It is 1 again. We have the same thing going on. We pretend x1 is a constant and goes to 0, and we take the derivatives here. And I should say technically this is going to be negative because these curves are negative. So it's technically -1. Sometimes we ignore the negatives. So if you gave me 1, I would not be, there wouldn't be a problem there. But technically it's negative. Okay, so that was an easy one, right? Just 1's in front of this. Now, let me introduce you to the first type of function that we're going to talk about. Is everyone okay with this screen? Okay. I'm going to introduce you to the first functional type that we have, and that is known as linear or perfect substitutes. So we just have, sometimes it's referred to as 2 different names, linear or perfect substitutes, depending on your book and everything. So I give you both so that you know them to hear them later. So here, an example for us might look like utility is equal to ax1 plus bx2. As we go through this chapter, it's going to be really, really important that you recognize which functional form, the equations are in. So if you see something that looks like, just x1 plus x2 with some constants in front of them, it's always going to be linear. So there's no exponents up here. They're not being multiplied together. It's just something x1 plus something x2 is always linear or perfect substitutes. Okay. And for the MRS, well, this looks like, take the partial derivative with respect to x1. It's going to be a. And then the partial with respect to x2 is b. This is a constant MRS and something we can use as we go forward. If I give you one of these equations with numbers, instead of really thinking about the partial derivatives, you can just take those numbers, a over b, depending on what I give you. So there's kind of like a shortcut here. Makes our lives a little bit easier. All right, example. Maybe we have 5x1 plus 4x2. Again, this is linear, perfect substitutes. And can someone tell me the MRS here?
5/4.
Yeah, good. So again, just the constant in front of x1 over the constant in front of x2. 5/4, divide it if you really want to. And I'm going to draw this with u equals 20, just to give me a number. The line is just linear, just a straight line in your, on the graph. So also when you see a straight line, you need to identify that that's linear and perfect substitutes. Now it's called perfect substitutes because we can kind of easily substitute between these two goods. And I'm using the same word in the definition, but we can replace one with the other relatively quickly or easily. So let's say that we have, I'll start here, 4x1 and 0x2. And I'm trying to think, sorry, numbers aren't going to work out perfectly. So let's say instead of 0x1, we want 1x2 for some reason. Well, we just, we put, 1 for x2, and we're getting 4 units of utility from it. We take that away, and we're left with 16. I know this is, the math is not too important, but we're able to substitute fairly easily. This is going to be 16/5, technically. The math isn't important here. But going between, 0 units of x2 and 1 unit of x1, we can substitute very easily, is what the idea is. We can use these goods in place of one another is what I'm trying to say. Maybe just forget about all of this down here. So might be like olive oil and canola oil, something like that. We can substitute them. I'm just going to show you in your notes. Again, there's a lot here that you're not going to need. This is a lot. What we're really looking at is this top one. There are different possibilities here that we are not going to go through. And this first one says goods in quotations. Now, when we talk about really our utility, we're typically thinking about goods that we like, goods that we want more of, fruit or shoes or anything like that. But we could possibly, like here, talk about bads or bad goods we talk about in economics. And what that means, these are things that we don't want more of. we would prefer less of. So homework and quizzes, or parking tickets and traffic. These are things we want a lot less of. So that's just a possibility. We aren't really going to go through it. So this first one is what we are focusing on and what we're going to do. So first one, again, want to know what it looks like, what the graph looks like, and also what the MRS is. Just to give you an example, like you might see, you know, a lot more lines for different levels of utility, but I might say, okay, with this graph, what kind of preferences do we have? Because they're all linear and downward sloping here, we'd say perfect substitutes, linear. That's number one. There's 4 altogether, these preferences, but one of them we don't really go through too much. I'll show you what that looks like probably on Wednesday. The next one has a name called Leontief, which just after the first, you know, guy that talked about this, or one of the first. And we can also call this perfect complement. The form for this equation always looks like U equals a minimum of AX1, say BX2, just putting these letters in. This minimum tells us we have Leontief or perfect complements. It's a weird function. It's always like this. And because it's so weird, you know, we have the minimum here, and I'm going to show you what it looks like. It looks weird when we graph it. The MRS is actually something we can't find. So you can say there's no MRS, or you can say it's undefined. Either way, that's right. So I could ask you, you know, on a quiz or on a problem set later on, like, what's the MRS for this Leontief function? And you tell me there is none. There's nothing you can actually find here.
What is that first word, Professor?
What was that, I'm sorry?
What is that first word before perfect complements?
It's Leontief. It's the guy's name.
Okay.
Yeah. So just sometimes books refer to it as Leontief preferences, and that's why I want to give it to you. Your book really uses this. I'm going to give you an example, and I'm going to kind of draw it. It's weird when we draw it. The U equals minimum. And what is it? 2x1, comma, 3x2. So when we go through this, we go to graph it. Really not going to ask you to graph it too often, but I'm just going to show you what it looks like. We need a number for utility, and maybe that's 6. So we're going to pretend that each one is 0 and look at the other one. So if we pretend x2 is 0, we just look here, or not 0, but we just focus on one of these. So 2x2. We're going to say 2x1. I'm sorry, 2x1 equals 6. We solve for x1, and that's 3. I'm just going to put a little mark on my graph for 3. Do the same thing for the 3x2 and equal that to 6. x2 is 2 here. And we have a point there from what we just did by just setting them both equal to 6. Now what we do is we take that point and go horizontally to the right and also vertically upward. This looks like an L shape. This is the functional form of this function here. So we have something like this where U is equal to 6. We can have higher ones though. So another one might be here. U is 12 or something like that. You can keep going upward. So anything upward is going to give us more utility still, but again, they look like L's. Now what this does is maybe this is our perfect cup of coffee. And to get that perfect cup, we want 3 shots of espresso, so 3 shots, and 2 sugars. That makes us happiest. And we call them complements, perfect complements, because they go together to make this good, right? We need them in a fixed proportion. If I don't have this proportion, I'm really not happy. I'm very picky here. So I need 3 shots of espresso and 2 sugars, and that's this point. Now, for instance, let's just say I get a barista that doesn't hear me right, and they give me 4 sugars with my 3 shots. Well, I'm still, that point, 3 shots of espresso and 4 sugars, I'm still in the same utility function. Having one more, or more of one good doesn't make me happier. I want the fixed proportion, 3 and 2. So that extra sugar doesn't make me happier without more espresso. If I got more espresso and had these more sugars, I would be happier. So like if I jumped up to a different point, say I had, I don't know, 4 shots of espresso. This isn't, this would be 6, sorry. I was just making up numbers, I shouldn't do that. So say I end up with 6 shots and 4 sugars. Well, that would make me very happy. And technically, this isn't drawn right, but it should look like this. As long as I get more of both of these, I will be happier and move up to a different indifference curve. But if I only have more of one, I'm stuck on this first one because I don't want that extra sugar if I don't have more espresso. So having this extra sugar doesn't make me happy. All right, so you need to know what these look like, these L shapes, and you also need to know, what the formula looks like, minimum.